Yeah, cut the tube a little weird. Hey Chris, do you know Nicole Putnam? She's your year, I believe, in Arizona. Nicole Putnam.
So she was a grad student last year?
Oh, she still is.
Oh, okay. It doesn't ring a bell, but I knew most of them. Like, there weren't that many girls. A lot of girls.
Astronomy.
Oh, okay.
I mean,
It doesn't ring a bell.
still looking at money for spring.
But,
Yeah, she's applied here to our lab. Computer science.
where did you do your undergrad?
University of Rochester.
Probably, well, maybe next week.
Yeah, Rochester's a cool school. There was actually quite a few people in Arizona that went to Rochester.
Yeah, I miss
He's one of them. Did you ever?
I totally remember the problem. Yes. The problem was
Probably
you
okay.
hang the rock.
Yeah.
You know how where you pick the ones where the next you get like a surface.
Yeah.
Well, Bob actually threw
That
some
idea
states
of concept in the
recently.
middle.
I think they're going to do less
Right.
live.
Otherwise you eliminate.
No, it's not. When you change the size of it. Ran our interview tour. Well, she's not very popular one.
No, this girl's not very blonde. She's brown hair. Yeah. You might have to rate, you know, which one's she's blonde.
Okay. Let me just. Okay. Are there any questions or comments before we get started? So just let me do a quick show of hand. Just let me install this. Okay. Okay, it doesn't matter. I'll just leave it at the table. How many people took between 0 and 5 hours to do the lab?
The actual implementation, probably. Writing it up took a while.
I mean total, end to end. So nobody. 5 to 10? Okay, most people. 10 to 15? Oh, wow. 15 to 20? Okay. So it's sort of sometimes. This was a hard lab, actually. I admit up front. The next homework is a lot easier. It's 4 problems off Eennlb. We're going to do next week. Um, and just also another show of hand to see, how many of you find the TA useful and the office hours useful? How many of you went to visit office hours this week? Oh my God. Okay, very excellent. TA is very good. Okay, very good. I always, every semester, the department normally doesn't allocate a TA for this course. And every semester, like a week before classes start, I have to go and beg. And at that moment in time, everything is settled, and they say, yeah, we have a little bit of money available. You could have a half-time TA, and then I grab it, and that's how we ended up with Cindy. And last time it was the same story, and the time before that it was the same story. So it's always a bit of a struggle, and I'm trying to figure out whether it's worth the last-minute fight or push to get the TA. And if you guys find it useful, that's good. So what I'm going to talk about today is filter design for 2D, and I'm hoping that excuse me, this is it. This is all the 2D signal processing stuff we're going to talk about, and that hopefully beginning next week excuse me, we're going to start talking about image processing. Start with basic of human visual systems, and then move on to enhancement, restoration, imaging systems, quantization sampling, and other fun stuff. So this is the last of kind of the basics. If you don't know what filters are, you wouldn't know, or how they were arrived at. You wouldn't know how to design one if the need arises. So what we talked about last time was there's basically 3 steps in filtering. One is figuring out what your specs is, and that's very much an application domain type thing. Whether you are designing a filter, let's say for a cell phone to reject out-of-band kind of signals, or whether you're designing something for a VCR, or it's just very much application dependent. By the way, how many of you attended the talk by, I can't remember the guy's name, on Wednesday from 11 to 12 in Corey Hall by the ex-FCC guy? There's this man in his 70s almost, white beard, white hair. He had spent his life at FCC, and the topic of the talk was spectrum property rights. In other words, right now there's a lot of demand on the spectrum, and different services chew up different parts of the spectrum. There's a portion military uses, and there's a portion for emergencies, the police, this, that, and the other. And as you know, the government of U.S. FCC auctions these, and and he was talking about the notion of owning a piece of the spectrum and how difficult it is to define that, simply because even when you define a simple thing like an AM radio, you could say, okay, this is my spectrum band. What happens is that in summertime, for example, in wintertime, for example, on the East Coast, there's a ton of interference from European signals bouncing off the ionosphere coming out, and you can almost listen to radios from Europe and the East Coast of the United States because of the reflection off the ionosphere. And in the summertime, it all becomes noise. So there's a time varying nature to the ownership to the spectrum, and to the ownership, and therefore that's what makes the ownership of the spectrum very difficult. And a good part of his talk was about filters that are in receivers, and how the companies like the fixed wireless guys who are trying to compete with the cable and the DSL companies to put a high-speed modem in your homes, they initially put a really cheap receivers to minimize cost, because they were adjacent to the satellite radio spectrum, like the Sirius and the, what's the name of the other one? XM, right. And then the Sirius and the XM guys decided they're going to put repeaters on Earth, on they're not just going to be satellite, but in urban areas they're going to put repeaters. And as soon as they did this, the signal spilled over to the adjacent band, which is what these fixed wireless guys were using. And so now the receivers they have to design was much better. And what does that translate to in our discussion? That means they have to have a much sharper kind of a filter to reject out-of-band kind of signals. And that that directly translates into cost and implementation cost increases and all that. in any event, for people who think that filter design is out of fashion and it's irrelevant, that's really not the case. It's still quite a bit of, it's a done deal in terms of designing filters. Nobody does research in that, but it's still used in day-to-day applications to reject out-of-band kind of signals and to define the notion of interference. Anyway, the bottom line for this guy's talk was that defining ownership of spectrum is very difficult, and the government is very hesitant to either come up with a methodology to say, okay, if you pass this test, then this piece of spectrum is yours, and anybody who infringes on you using this test, they're infringing, and you can sue them. So the government is very hesitant to come up with those guidelines because of the difficulties in measuring property rights for spectrum, and he kept referring to it as it's as if somebody came to your house and invited themselves and started drinking beer in your living room, kind of by spilling over from one band to the other is the signal kind of coming over. Anyway, quite interesting stuff. What I'm going to talk about today is really very quickly 3 methods of designing 2D filters, and 2 of them are very similar or just extensions of one-dimensional techniques, and the third one is a transformation technique by McClellan, who, by the way, is the same fellow who designed the Parks-McClellan filter in one-dimensional signal processing. And then that'll be the end of the discussion on 2D FR filter design, and we'll move on to other stuff. So let me just begin with saying a few words about filter specs. I lost my good pen. Yeah, here it is. Okay, so I'm going to start with a one-dimensional example. If I have a low-pass filter, then I can, as a function of omega, I can talk about the magnitude of h of omega satisfying certain constraints. In particular, I can talk about a region in the frequency domain here, which we call passband, where we require h of omega to be within a certain range between 1 but no less than 1 minus delta p. This is the region that, because it's a low-pass filter, this is the region you want the filter to pass the signal. And then you can also talk about a different region, which is called the stop band. This is the band in which the filter is going to stop the signal, and you want the magnitude of h omega to have a different set of different set of characteristics. You want it to be very small. You want not to let the signals go. And this band in between omega p and omega s is just called the transition band. And it allows, we don't put any conditions or requirements or specifications on the filter here. And for stop band, let's say we say that this has to be smaller, the magnitude of h of omega has to be smaller than delta s. So in general, delta p and delta s, they're called ripples. And this is called passband ripple, and this is called stop band ripple. And they could take numbers like 0.01 or 0.001, or they need not be the same anyway. They could be different. Okay. So now we move on to 2 dimensions, and you can talk about 2-dimensional specifications just as easily, more or less the same way. Okay. So 2-dimensional specs. So now, instead of having as a function of omega, we plot something in the omega 1, omega 2 plane, and instead of having a passband frequency and a stop band edge like omega p and omega s, we're going to have a passband contour and a stop band contour. So we call this C sub p, and we call this C sub s. This is the passband contour. So this is again a low-pass filter, but in 2D. And basically now our specification becomes something like this. We want magnitude of h of omega 1 and omega 2 to be between 1 and 1 minus delta p for all omega 1 and omega 2 that are inside C sub p, inside the passband. So this is our passband region. And then for stop band, we'll have the following thing. We want magnitude of h of omega 1 and omega 2 to be smaller than delta s for all omega 1 and omega 2 that are outside C sub s, the stop band. So this would be the stop band region. And let me just use a different color, like green. This would be the passband region. Okay. So similar sort of ideas hold. And you can also have what's called a band pass filter rather than a low pass filter. And any questions on this before I move on? Okay. So you can talk about band pass filters, and in 1D it would look something like this. You pass a signal between omega s and omega p, and you reject everything else. And the equivalent of that, so this is in 1D, and the equivalent of that in 2D would be something like this. This is omega 1, omega 2 goes from minus pi to pi, minus pi to pi. We're looking at the frequency response. And so you stop the signal from passing through here, and you stop it from passing through here. So it's 0, 0, 0 there, and you pass the signal here. So it's 1 in this region. So passband, you pass the signal in the green, and you stop it in the red. Okay. Simply because there might be some characteristics, some specific kind of features you're looking for in that frequency band. And then there's also, I'm not going to talk about it, but there's also band stop, where you're letting all the frequencies go through except for one band. For example, what would be a typical example when you use band stop filters in 1D? If you want to try to get rid of 60 hertz interference, you just put a filter that you have a signal, you want all of it, but there's this big spike at 60 hertz because of whatever interference. So you pass it through a band stop filter that passes everything except for that region around 60 hertz. In 2D, you can also have a different kind of filter that whose equivalent doesn't exist in 1D, and that's a directional filter. Because the notion of direction doesn't really exist in 1D, but it does exist in 2D. So you want to pass frequencies along a certain direction and reject other frequencies along a different direction. So, and I think one of your homework assignments is just on that. So you want to talk about directional filters. Can't remember now. I think you might have a MATLAB assignment just on this in a week or two. So what what it is you, for example, you want to draw a line like this. Okay. And again, this goes from minus pi to plus pi. So you pass these, and then you stop the rest of it. Okay, and you could say the angle is theta, or etc. So in images and in two-dimensional signals, if you have features that are predominantly horizontal or predominantly vertical or predominantly at an arbitrary angle, you can either eliminate those or accentuate those and try to catch the edges and the directions along a particular direction by using a directional filter. Or if you're doing two-dimensional signal processing, you want to know, you have filters in a plane and you want to know which direction, let's say there's waves coming at you and you want to know which direction this wave was coming from. You can have a series of filters like that along different directions, and then look at the output and say, the output of the angle theta is largest, so there must be some signal coming from there. And back in the mid 80s, where we were deeply involved in the Cold War, and we were in the business of 3D verification. For example, at Lawrence Livermore, a bunch of my friends were working on designing adaptive directional filters. They would implement them underground, and in order to listen to the Soviet nuclear explosions underground, and figure out what direction the signals are coming from, and whether or not they're doing any nuclear testing or not, whether or not they can the signals are arriving from this part of Russia or the other part of Russia, or whether it's maybe China doing the tests, etc. So this is used for detecting the direction at which signals kind of are arriving. And it's also used actually in image processing. It turns out that there's a notion of directional subband coding for subband coding, which is a technique for image compression. David Taubman, in I think 1993 or 4, he and I published a paper on subband directional filters as well. So there's all kinds of 2D filters one could think about designing, and what are some of the techniques that we're going to use to do that? There's 3 basic ways of designing FIR filters, and we're primarily concerned about finite impulse response filters because they can be done with 0 phase or linear phase with a simple symmetry constraint, and also they have no stability issues. The first technique I'm briefly going to talk about is the window, and the extension from 1D to 2D is very straightforward. The second technique is frequency sampling, and again the extension is very easy. And then the third technique is design by transformation. And I'm going to, this is a technique that McClellan, who is now at Georgia Tech, came up with many years ago. And this is something, the equivalent of which in 2D doesn't exist, but essentially the idea is let's transform the problem into a one-dimensional problem, design a good filter in 1D, and then we'll get an answer in 2D. So let me begin real quickly with the window technique. And again, this is pretty much a review of 123. You start with an ideal frequency response. Something that you want. Suppose somebody has come to you and says, I want a brick filter. Well, we all know that's an ideal frequency response, and if you really wanted to get that, you would have to have an impulse response that's sync, which is not only IIR, it's an IIR filter with non-rational transfer function. So forget about that, but still you can dream of having an ideal thing. And then pick the inverse discrete time Fourier transform of that. In the case of this thing, it could be, for example, a h of n, which is a sync function. Okay, and it could be infinitely long. And let's just recall this thing h sub d of omega. We call this thing h sub d of n, the desired infinitely long impulse response. And now, because this is infinitely long and it's an IIR, then to make it FIR, we just multiply h of n by some window function w of n. And this guy is just a window function, right? So all of this just in a very straightforward way translates into 2 dimensions in the following sense. If you can roll up, please. Thank you. So we just do all those same steps, and we'll have h of n1 and n2 being equal to a window function n1 and n2 times h sub d of n1 and n2. This window function could be very simple. It could be just a rectangular window that basically just truncates this IIR filter. It could have some other fancy shapes. It could be a raised cosine window, a Hamming, Hanning, Blackman. There's as many windows as your heart desires. Just so that I can have a quick understanding of how much you've been exposed to this before. How many people have heard of the window design technique in FIR filter design before? Oh, fantastic. So we won't do all over it too much. So really quickly, if this is your h of omega, the desired magnitude ranging from minus omega p to plus omega p, and this is your h sub d of n, which is a sink type thing. Then you multiply it by window function, which would truncate it by this. This is your window function. And essentially by doing this multiplication in the time domain, you're convolving the Fourier transform of the window function with h of omega. So the resulting, this is h sub d of omega, sorry. So the resulting h of omega that you get as a magnitude of it is going to be, so here we're going to be convolving w of omega with h sub d of omega. And generally speaking, the longer the duration of this window is, the more the Fourier transform of the window is going to be like a delta function, and therefore a delta function involved with h sub d of omega is going to keep h sub d of omega as intact as possible, right? The shorter this box function is, I mean, what is the Fourier transform of w of n, the window function? If it is a rectangular one, it's a sink. So the shorter this w of n is, the fatter the sink is, and when you convolve that sink with this thing, you're going to get a big transition, a slower transition, some ripples here, and a slower transitions back. Okay, so and you can also have similar arguments with other window functions. So so the duration and the shape of this guy determines how good the final h of omega looks like. So the window, the shape, the length of the window, let's just write that down. The length of w of n and the shape of it determine how good h of omega at the end ends up looking like. So how do we translate all of these things in 2D? Well, first of all, in 2D, we're very much interested in linear phase or zero phase kind of filters. So let me roll back, please, just a tiny bit. So 2D windows, generally speaking, if I have an h of omega, it has a magnitude and it has a phase. And linear phase means that phi of omega, this guy here, is linear in omega. That's all that means. And zero phase means phi of omega is just 0. So in this case, if I were to plot as a function of omega, phi of omega, I get a line. And in this case, if I were to plot phi of omega as a function of omega, I just get 0. Okay? So we don't necessarily, so in our case, if we can easily show that when you're writing down the product of, so if you have h of n1 and n2 equals h sub d of n1 and n2 times w of n1 and n2, that's your two-dimensional window, we know that if this is a zero phase window, and this is just a desired impulse response, if h of d is zero phase, and if w is zero phase, then h of n, the resulting h of n1 and n2 is also going to be zero phase. So if you're and the same argument is true, by the way, with linear phase. If this is linear phase and this is linear phase, the final thing is linear phase. So if our goal is to design linear phase filters, we need to do no more than starting with an impulse response that's linear phase and starting with a zero and a window that's linear or zero phase.
Just curious.
What are some of the applications where you would want like linear phase?
Almost
bevel?
all image processing applications. Otherwise,
Really?
Yeah. Yeah. Otherwise, your edges all get blurred up. You almost, yeah. I haven't seen many FIR filters used in image processing. In fact, even when you do subband coding, that's you want to impose linear phase in image compression because again, it messes up the edges of images. The edge, as I said earlier, is a transition is a sharp transition, and the way you, from a Fourier transform or Fourier harmonics point of view, the way you generate it is you have a bunch of sinusoids adding up with the right phase. They have to have the right phase with respect to each other. If that gets filtered and the relative phase of the sinusoids that are adding up to make the edge get mixed up because the filter wasn't linear phase, then the edges get blurred. And you can all see why linear phase makes the relative phase of these things to be preserved because it delays, because delay is the derivative of phase with respect to omega. So if you have linear phase, all the sinusoids get delayed. The derivative of this thing is, look, let's bring back here. If you have linear phase, the derivative of this thing is constant no matter what omega you're at, and therefore the amount of delay between the sinusoids remain constant as they go into the filter. As the relative shift is the same going before and as coming out after, because they got delayed the same amount because this was linear phase. So the linear phase is a pretty important property. We almost exclusively talk about using linear phase filters in image processing. One of the things you might say is, well, how come we talked about this boundary condition stuff and all these other things with PDEs and difference equations, which was IIR filters? Well, those also get used in image processing. For example, in computer vision, a clear example of it is anisotropic diffusion processes, which Malik and Perona came up with in late 80s. That uses essentially a PDE that recursively processes, but that's really done in order to kind of segment an image, and to make the some of the features that are less important go away and the features that are more important show up, etc. So there is some applications where you use difference equations. Solving PDEs in science and engineering applications, in mechanical engineering, heat transfer, heat propagation, etc. Those also use the same kind of thing. But for images where you care about edges, most of the time you use linear phase or zero phase. Okay, coming back down here, so what are some typical windows that we can use? As I said, there's thousands of them, but we don't bother about writing them all down. But let's talk about the Kaiser window because it has some knobs that one can easily tweak in order to extend it to 2D. So let me write down Kaiser window. It's in the analog version of it, not even the discrete, is given by I0 of alpha 1 minus t over tau squared over I0 of alpha, and I'll define I0 in just a second, for t, magnitude of t smaller than tau, and it's 0 otherwise. So roughly speaking, the duration of this window is 2 tau. And alpha is just a knob that trades off the main lobe width of the window with side lobe height. I guess one thing that you want to walk away with in this picture, just a reminder of 123, is the main lobe width of the Fourier transform of the window function. In other words, the main lobe width of this tells you how long the transition takes, because you're convolving this with h sub d of omega. So the fatter the main lobe width of W of omega is, the Fourier transform of the window is, the longer the transition is, because you're convolving it with this guy, right? And then the second attribute of this window is the side lobe height. If this guy has a lot of side lobe height, as you're convolving the Fourier transform of this thing with this, when you're here at these positions, if there's a lot of side lobe up and down, there's going to be a lot of ripple here, and a lot of ripple here, and a lot of ripple here. So, and when we teach 123 and 1D, there's a whole lot of discussion. Okay, well, if you use, rectangular window, you get very good main lobe width, but terrible side lobes. If you use, if you use raised cosine Hanning, etc., the main lobe gets bigger, but the side lobe gets smaller. And so people are all confused. What window shall I use? Kaiser offers a very nice compromise or trade-off. It has a knob alpha. It's just like a knob on your stereo. You can tweak alpha, and by doing that, you can do this trade-off between main lobe width and side lobe width of the Fourier transform of your window, which translates into the trade-off between transition width of your final filter and the amount of ripple that you get in passband and stopband. Okay. And I still haven't defined I0, just for sake of completeness. I0 of x is just a modified zeroth order Bessel function. And there's various ways of defining it. One of them is to say Bessel function. One of them is to say it's a solution of a differential equation. Another way is to write it in terms of series. I0 of x is summation from I equals 0 to infinity of x to the power of 2i. 2 to the power of 2i, and then I factorial squared. Okay. And you can look up the definitions of zeroth order Bessel functions, these series expansions in any CRC handbook, mathematical CRC handbooks. Okay. So now that we have this Kaiser window that has this knob alpha that allows us to do this trade-off that we just talked about, how do we translate that in 2D? It's extremely straightforward. You just say, if you can roll up, please. So the 2D window is just come up with a continuous time 2D window, and then sample it to make it discrete. So the continuous time, I would say WA of T1 and T2 is just WA of T1 times WA of T2. That's one simple way of doing it. I'll show you a second way in just a second. And then step 1 is this, and then step 2, sample this to make it discrete. Okay. So you say WN1 and N2 is just WA of T1 and T2 with T1 equals N1, T2 equals N2. And this is for N1 and N2 in some region of support, R sub W, and it's 0 otherwise. So ahead of time, you've kind of decided that as a function of N1 and N2, you've decided that this is not a good picture. Let me just move on to the next page. Great. So you've decided that as a function of T1 and T2, this goes from minus tau to plus tau in this direction, minus tau, plus tau in this direction, and you first come up with WA of T1 and T2, and then you sample it. And it's supposed to be equally spaced, even though I'm not doing it equally spaced for some region. So in essence, the discrete time window that you get, W of N1 and N2, is WA of N1 times WA of N2, where this is just a sampled version of WAT. Okay. And you can also show, because this is called separable, right? Now we have a window function that's separable, and the Fourier transform of this guy is just the Fourier transform of this times the Fourier transform of the other, and WA of omega 1 times WB of omega 2. So that's one simple way. You have a one-dimensional window, just multiply it in dimension T1 and dimension T2, and from one-dimensional window to get to the two-dimensional window. And the second way of doing this is just rotate the one-dimensional window to get the two-dimensional window out of it. So, are there any questions? Let me pause for a second. Yeah.
Is it because they're separable that you multiply the
Right. Right. I think we showed that almost lecture 1 or something like that, or we just mentioned it. You can prove it very easily as a Fourier transform property. And right. We also I think what we showed at the beginning of the class also is that if your impulse response was separable, you can do the computation a lot faster than if it wasn't separable. So another way to do 2D windows is just the rotation business. In other words, rotate WA of T to get WA of T1 and T2, and then sample WA of T1 and T2 to get W of N1 and N2. Okay. So what do I mean by that? Well, what we mean is WA of T1 and T2 is just WA of T, but rotated. So replace T with square root of T1 squared plus T2 squared. Okay. So now the picture that you get for W as a function of T1 and T2, the picture that you get for WA of T1 and T2 is something that like takes on the value 1 here and takes on the value 0 outside. Okay. And thank you. So now that I did the rotation, now I have to sample this. So what I say is W of N1 comma N2 is WA of T1 and T2, but sample that T1 equals N1 and T2 equals N2 for all the N1s and N2 that are in some region W, and it's 0 otherwise. Okay, so this is a circularly symmetric window, and at the end of the day, I'll show you now some pictures of these things in action. At the end of the day, when you use a circularly symmetric window, it turns out the H of omega 1 and omega 2, the frequency response that you get, it also has contours that are circularly symmetric. So let's take a quick look at that. That'll be chapter 4. Here we go. Okay, if you can just zoom in as much as you possibly can. Great. So this is an example of a do you think it's the circular symmetric or the separable? Separable. Like you can say right away, you can tell right away. By the way, can you guys in MATLAB? I bet you can do nice plots like that, right? Yeah, these are straightforward plots off of MATLAB. Do you feel yourself that you're getting more familiar with the image processing toolkit of MATLAB by doing the lab homeworks? Do you now know most of the commands and stuff? Because you have to search so long to find to find the commands that you want for it. Anyway, so this is a separable kind of a filter, and by contrast, this is a circularly symmetric. This is just a Fourier transform of the window function. We're still not talking about the filter. So this is W of omega 1 and omega 2, which is the Fourier transform of the window function when you do the rotation business. And so this is a um, um, that's kind of an interesting picture. I'll just quickly talk about it. What you see here is a circular symmetric window where with the one-dimensional filter was Hamming window where you rotated it, and the expression for Hamming window is shown right here. Some people call this raised cosine. It has a shape of a cosine that gradually dies down and goes to 0. This is the for tau equals 8. Uh, um, out here is the Kaiser window with alpha equals 1, and down here is the Kaiser window with alpha equals 3. So as you can see here, yeah, I don't know if it really shows up in your screen or not, but the main lobe of this guy is smaller than the main lobe of this guy. But the ripple, the side lobe of this guy, is higher than the side lobe of this. So as we changed alpha from 1 to 3, which we did that trade-off that I just talked about. Here's here's an example of a low-pass filter that was designed where we used a one-dimensional Kaiser window, and in this plot, what you can see is the well, here's there's a 3D visualization of the 2D frequency response, and this is the contours of the frequency response, right? How do we compute the contours? It's just isocontours. You cut it and find the points at which it crosses a certain level. And looking at this and looking at that, do you think this was a separable 2D Kaiser window or circularly symmetric? Separable, because it kind of has a squarish look to it. By contrast, if you look at the isocontour of the circularly symmetric one, you see it's DM circle. It's good circle, right? Compare that with this, okay? And this is the circular symmetric 2D filter, h of omega 1, omega 2. You can see, you can detect the circles with your eyes even. And this is the separable one because it has these edges, as you can see right there. Yeah, sure.
I was just curious, I mean, why would somebody make a point to make that, like, slight depression in the center and then that other, like, hump in the middle?
This one or the other one?
Like that one right there, for instance. I mean, it seems like if you want to make a low
the hump
pass.
in the middle? I mean, why did someone do that?
Why would somebody do that, yeah?
They didn't want to do it on purpose. It came. It's the ripple. It's the ripple of the Kaiser window in the middle. You can't, from an approximation theory point of view, making the thing absolutely flat here and absolutely flat there, it's not impossible. You need to have a lot of terms. That means that the FIR filter ends up getting bigger and bigger. Each coefficient in the FIR filter is a knob. The more knobs you have, the more freedom that you have not to have these junk on top and at the bottom. And so it's kind of like it's giving yourself more degrees of freedom always buys you better frequency responses. But if you don't and you have a finite number of coefficients to play with, this is kind of what you get. Absolutely a good point. This is not by design. It is by accident. Nobody would wonder. That's why in the passband you want to bound your ripple delta p to be smaller. And if this is no good for your application, you make delta p to be 0.4 zeros and a 1, 5 zeros and a 1. And you always have to be wary about applications where people tell you that you want to have a lot of zeros. Or applications in real life where people say we want to have non-failure mode probability of 99.9999 with 7 nines after the decimal. It's like, well, what are you trying to accomplish? But nevertheless, you can achieve those by having larger number of taps. Come back here. This is an example of a band pass filter using using separable windows and Kaiser. And this is the contours for it. And you can see it's kind of squarish looking here. In between, all hell breaks loose because you're transitioning from this band to the other band. And if you use circular symmetric, again, compare these contours, especially in the middle, with these contours. They're much more circular. Okay? And this is the frequency response of a circular symmetric bandpass versus separable. And I'm going to show one last picture, and that might clarify Chris's point a little bit. So here's an original Vegas picture. When I was a student, there were only like 4 pictures you could process as an image processing student. There was the IEEE lady, which it's not even in this book, but some of you have seen it. She has this old style, I wouldn't even say 50s, I'd say 40 or maybe 30s, 1930s. Straight hair coming with a curl down and a straight hair coming. I think the only woman in the class the 2 women can understand what I'm talking about, right? It's really old. I mean, it's one of those old styles that it still never came back in fashion, even in the 2000s or whatever. And then there's the Vegas picture, and then there's the cameraman picture, and what was the 4th one I was going to say? Lena, right? Lena, I forgot. Lena is the most widely used. Anyway, so this was the Vegas picture, and this is if you process it with a linear phase. This is the original. This is if you process it with the linear phase. And this is what happens if you process it with nonlinear phase. If you can just slightly zoom back. Okay. No, I just want these 2 to be shown as big as possible. Zoom in. Okay, great. I think the point gets driven. If you have the book, look at 4.1 in Jalen's book. So this kind of shows you the example of of processing images with linear phase versus nonlinear phase. Okay.
What are some of the features, I guess, between A and B? Because that's the difference between 0 and linear phase, right?
No. A was the original.
Oh, A is the original.
That's
okay.
right. B is just applying. In this case, he does 0 phase. There's no difference between 0 phase and linear phase, by the way. So if I do 0 phase, I've gone an extra mile in making the phase actually 0. But 0 phase and linear phase are just as good, because it's the derivative of the phase. Remember, d phi omega d omega, that's delay, right? The derivative of phase of the Fourier transform, that's the delay of that filter. And you want the delay to be constant no matter what the frequencies are, because what that does, it delays all the frequencies, all the sinusoids of different frequencies the same amount. So if their shift was this much before, their distance is the same after the filtering process. So that's really what preserves the edges. Is that point clear? Okay, so that's all I want to talk about in terms of the window technique. Next, I wanted to quickly talk about frequency sampling. Again, it's straightforward extension of one dimension. I lost my pen again. No, this is good. Okay, so frequency sampling technique. And just like it sounds, you go to the frequency domain, omega 1, omega 2, and you're going from minus pi to plus pi, minus pi to plus pi. And let's say you want to design a low-pass filter that passes these bands and stops all these other bands. So it's 1 everywhere here and 0 everywhere here. So I'm going to say stop band is here and pass band is here. Okay. And how do we do that? Well, the way this thing works is you just sample the frequency domain at equally spaced points. Pretend those are equal. It's a grid, and you take inverse DFT of it, and you get a filter. So you sample this 0, 0, 0, and then 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, etc. And then you have an array of zeros and ones. You take the inverse DFT of it, and you get an array. Let's say you sample it at the 10 by 10 point, or let's just be realistic. 16 by 16 samples, you take the inverse DFT of it, you get a 16 by 16 array, and that's it. That's your filter. Is that a good technique or a bad, and why? What's the frequency response of that filter? That resulting 10 by 10 FIR filter we just got, what would be the frequency response of it? Well, at these points that I sample it, it'll be exactly what those samples were. And in between, all hell breaks loose. Who knows what it does? It could go up, down, ripple, everything. So, so let me just write down the basic steps. You sample the 2D Fourier space on a grid, let's say m by m grid, m by m equally spaced points. And from Fourier theory, you know that the signal that you get will have a DTFT that at those samples will be what you force them to be, but in between the samples. So if I were to, for example, figure out if it's probably going to be 0 at this point, at 0 at that point, but the DTFT in between these points here could be anything. Okay? And then take inverse DFT to get the m by m FIR filter. It's the equivalent of the 1D version where you start with an h of omega as a function of omega and you sample it out between 0 and pi and take the inverse DFT in one dimension. And let me just show you some examples of filters using that. So let's look at figures 4.10 through 4.11 in J. Lim's book. so here's what you get. If you can zoom in, please. Okay, so so this is a frequency response from minus pi to pi, minus pi to pi, and I wanted to design a circularly symmetric low-pass filter. So the filled circle in the middle, I want to pass these points, I want to make it 0. And this is a little bit more sophisticated than I just explained. He allows for a transition band. You can allow for these points in the middle to be like 0.5 or something like that, just to make your job easier. You don't have to do that. And after you do it, here's a 15 so after you do that, this is the filter that you end up getting. 15 by 15. Let me see, how many points is it? Yeah, it's a 15 by 15 low pass filter. This is the frequency response. You can see it has a hell of a lot of ripples, and this is the contour plot for it as well. Not really very good. It's not even as good as the Windows design. Yeah.
I'm just a little confused. I thought we were. So you're sampling you create this grid of frequency samples, and then you set some of them equal to 1 in the middle and some equal to 0 on the edges. So that, I mean, isn't that going to be your frequency? That's like your transfer function, right?
No, because I sampled the frequency response at that. The samples of my frequency response at those samples will be exactly 1, will be exactly 0. But in between the samples, remember when I talk about frequency response, h of omega 1, omega 2, omega 1, omega 2 are continuous variables. I've only made samples of omega 1, omega 2 just at those locations behave the way I wanted it to behave. In between those that I didn't sample, it goes to hell. It could do anything. And that's exactly what's here. Here, at those samples, it's exactly 1, and here, at those samples, it's 0. It's between them that things didn't go back, which causes the ripple. Again, omega 1 and omega 2 are real, right? So just because, it's sort of like this, just because I sample the function those points, it didn't mean that in between those it's going to behave properly. Now, if instead of doing 15 by 15, if I sampled it more finely, let's say I did 30 by 30, this would look a lot better. But what did I just do? I made the size of my filter 4 times bigger. If I made it 60 by 60, that would be even better. But now I have a, wow, 3,600 point FIR filter. That's terrible. That's really big. I mean, have you got, I forgot whether in the radon and the tomography homework that you just did, they've done tomography, oh, then they've done the phase reconstruction. There you didn't have to do any filtering. Did you do any filtering in tomography one? No, not much. You'll get some filtering MATLAB assignments. I mean, most, for example, most filtering that you do for, let's say, subband image coding, you want the number of taps for your one-dimensional filters to be no more than 5 or 10, and for two-dimensional filter, no more than, I don't know, 5 by 5 or 7 by 7. You don't want to have so many taps, okay? Because the computation gets out of hand, because, yeah, and you can, many of the tasks that you want to accomplish can be easily done. If you didn't use the simple technique like frequency sampling. But you should be aware that if you do that, you get this kind of low quality filter. And if you can put back the camera on, and similarly the same thing for a bandpass filter. If you design a bandpass filter using this technique, you get all these ripples and bad stuff. And this is the contour plots that you get using frequency sampling. But don't despair, because we're going to talk about a slightly more powerful technique. In 2D, unfortunately, if you remember in 1D, there was a technique called the proximate clone optimal filter design using Remé's exchange algorithm and all those fancy things. And there was a theorem associated with that which said, if you give me a set of specs, then I can come up, there's a unique filter with minimum number of taps that satisfies those specs, and that it won't go any lower than that minimum number of taps. It was an excellent technique in 1D. It essentially killed all the other research in one dimension, which before that was highly concentrated on designing windows. That's why there were so many windows and so many names of windows floating around. So Parks and McClellan in 1972 came up with that one-dimensional optimal 1D filter, FIR filter design, and just knocked that field out. No more papers on filter design using windows. Unfortunately, that result doesn't hold in 2D. And once again, it's not surprising. It has to do with fundamental theorem of algebra not holding out in 2D. However, McClellan still came up with a technique called transformation. It can be shown to be optimal, but it's kind of a nice technique. And I'll spend hopefully the rest of today wrapping it up, so it doesn't have to spill to next week. But let me just tell you what that is. So 2D filters design. I lost my pen again. Using transformation. And just as the name implies, we're going to transform a 1D filter into 2D. So the basic idea is this. You start with h of omega 1 and omega 2, and you say that's equal to h of omega, with omega replaced by g of omega 1 and omega 2. Okay? Or another way of saying it is h of omega 1 and omega 2 is h of omega, where cosine omega is replaced by t of omega 1 and omega 2. And you'll see in a second why I call it cosine omega equals that versus omega equals this. They're all the same thing. It's just, it pops out easier. So given that methodology, the questions that come up is, number one, how to design t of omega 1 and omega 2. And number two, how to design h of omega. Well, how to design h of omega, this part, boy, there's a lot of rich theory that allows us to do that. There's optimal filter design that you can do that. So really the basic challenge then becomes how to design this guy T. Okay. So the first thing I want to say is, once again, I want to talk for 1 minute about zero phase or linear phase, because I want to end up with zero or linear phase filters, right? So first of all, in 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 one dimension, how is it that why is it the claim I want to make is this. I want to say if my h of n, the impulse response in this is zero phase, um, and if I impose certain condition on this guy t, the final filter will also be zero phase. So make h zero phase, make t zero phase, and h of omega 1 and omega 2 will automatically be zero phase. So before I get into that, I'd like to make one other comment about one-dimensional zero phase filters. Is it easy to design FR filters in 1D that are zero phase or linear phase? Extremely. Why? What do we do in 1D to make sure our filters are linear phase or zero phase? Exactly. A symmetry condition is all that you need. And I like to mention that because I've emphasized zero phase is so important in image processing, and yet if I don't tell you how to make the things real zero phase or linear phase, then you might be very uncomfortable and not be able to sleep tonight. So let's remove that ambiguity here right away. So the question that that I want to ask is the following: how to make h of omega in 1D be zero phase? Is that an easy job or a hard job? And the answer is, you can show that if the filter is zero phase, in other words, if I have an h of omega that's written as magnitude of h of omega times e to the j phi of omega, right? That means phi of omega is equal to 0 for all omega. Well, what does that mean? That means that h of omega is equal to h complex conjugate of omega, which means h of n is equal to h complex conjugate of minus n. And furthermore, if I assume that h of n has real coefficients, not complex, which is, I'm dealing with real images and I don't want to have complex coefficient kind of filters, that means h of n is equal to h of minus n. So what does that boil down to is that zero phase in 1D implies, and is implied by h of n being h of minus n. So if I just impose this symmetry condition on my one-dimensional tap filters, boom, my h of omega will be zero phase. Okay? So in order to have, in this transformation technique that I'm going to talk about, in order for me to have a shot of designing h of omega 1 and omega 2, my 2D filter to be zero phase, to begin with, I'm going to start with an h of omega that's zero phase. Okay? So coming back now to our filter design, so assume h of omega is zero phase. In other words, h of n is equal to h of minus n. And we assume h of n has 2n plus 1 samples, non-zero values. Okay? So what can I say? Well, in general, h of omega can be written as summation n from minus n to plus n of h of n e to the minus j omega n. But now, if I apply the zero phase constraint, which makes the filter taps symmetric, then I can pair up like h of 1 with h of minus 1, h of 2 with h of minus 2, and write this thing down as h of 0 plus summation n equals 1 to capital N of 2h of n cosine omega n. So here's the zero phase aspect of it coming in. Okay? And I can now rewrite this thing, if you can roll up a little bit, as summation over some other coefficients a of n cosine omega n, where a is related to h, and I make n go from 0 to n. Okay? So you can easily see that you can write down the coefficients a in terms of h of 1, h of 2, h of 0, all of that junk. I'm just introducing a new notation. And now I'm going to make another jump, and that is, this is a summation from n equals 0 to n of another set of coefficients b of n, but power in terms of powers of cosine omega. I'm writing cosine omega n as sum of the powers of cosine omega. And you all know how to do that, right? It's Chebyshev polynomials. Or Chebyshev, whatever, however you want to call this guy. And what do I, just as a quick reminder, you can write cosine 2 omega as cosine omega plus omega, which is 2 cosine square omega minus 1. Then you can write cosine 3 omega as cosine omega plus 2 omega, which is da 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 da. You can write it as, expand this out, and you get a bunch of other stuff, and then you can write it as 2 cosine cube omega minus cosine omega minus 2, 1 minus cosine square omega, cosine omega. So you can write down the bottom line. The reason I could go from here to here is that you can write down cosine of multiple integer values of omega n, as sum of the powers of cosine omega. And this is because of this relationship. And we already used that in 1D to do our optimal filter design, right? And why do I want to write it like this? Well, now you can see why at the very beginning I wanted to write my transformation as cosine omega replaced by t of omega 1 omega 2. So now I can do the replacement from here to here. I can just say h of omega 1 and omega 2 is h of omega with cosine omega replaced by t of omega 1 and omega 2. So now I can say that my h of omega 1 and omega 2 is summation from n equals 0 to n, and now I'm going to replace this cosine omega with the t guy, t of omega 1 and omega 2, the whole thing to the power of n. So that's my filter after the transformation. And what I propose is that if we make this guy t to be zero phase, then because we also made h to be zero phase already, we took advantage of that. We took the benefits of that. If t is also zero phase, you can easily show that h will become zero phase. Okay? So let's just do that. So can show, and I'm not going to show it, that if t of omega 1 and omega 2 is zero phase, and if h of omega is zero phase, which we assumed it was, and we used that to get to this point, then h of omega 1 and omega 2 will be zero phase. And that's good. That's very reassuring to know. So now let's do a little kind of a size argument. Suppose that t of omega 1 and omega 2 was itself a frequency response of another 2D zero phase filter. In fact, it has to be, because we assumed it's already zero phase. So it's a frequency response of filter t of n1 and n2. And suppose t of n1 and n2 is 2m plus 1 by 2m plus 1. Okay? And we already know h of omega was 2n plus 1 point. So what can we say about the size of h? Well, let's combine these things kind of together, right? Let's write down t of omega 1 and omega 2 in terms of t of n1 and n2. What do we get? Well, it's t of omega 1 omega 2 is just the Fourier transform of t of n1 and n2. So it's double summation for n1 ranging from minus m to plus m, and n2 ranging from minus m to plus m of e to the minus j omega 1 n1 e to the minus j omega 2 n2. So now I can plug this equation straight into this one that I had before, into this guy. Instead of having t of omega 1 omega 2, I plug in this long expression down here. So let's do that. So what I get is h of omega 1 and omega 2 is the summation n equals 0. Sorry, this is capital N. There was a typo here. To capital N of b of n, and now I'm going to replace this t guy to the power of n with the expression I have here to the power of n, which is double summation n1 minus m to plus n, n2 minus m to plus m of t of n1 and n2 e to the minus j omega 1 n1 e to the minus j omega 2 n2. And now, staring at this thing, what can you say about the size of h? What's the h of omega 1 and omega 2, by definition, is the Fourier transform of the new filter we're after, the h guy, e to the minus j omega 1 and 1, e to the minus j omega 2 and 2. What is the region of support of this h guy? It is n1 from where to where and n2 from where to where. Well, yeah, I'll give you a chance to take a look at it. Let me see if I can get any answers from you guys. Well, there's a power of n here. This little n goes from 0 to n. And so you're going to have e to the minus j omega 1 n1n. And n1 can go from minus m to plus m, and n can go from 0 to capital N. So what would be the powers that what would be the powers of e to the minus j omega 1 that I will experience? Yeah, it goes all the way from minus nm to plus nm. So this guy is a filter that's 2nm plus 1 times 2nm plus 1. So using this approach, if m was 1, which meant that t of n1 and n2 was just 3 by 3, and n was 10, which means my h of n was just a 21-point filter. Sorry, a 21-point filter. Then putting those things together, h of omega 1, h of n1 and n2 would be 21 by 21-point filter. Again, which is large. But the beauty of it, if you will, is that we managed to design a large filter by only designing a little two-dimensional filter T, which is only 3 by 3, and then a regular one-dimensional filter, right? So you can already imagine kind of what the steps are in designing two-dimensional filters, right? So here to sum it up, to design based on all of these things and roll up please. So what would be the steps you would want to take in designing a 2D filter using this transformation technique? Well, so these are the steps. You start with a set of specs. Specs in 2D, specifications in 2D, and then you either choose or design this little filter T of N1 and N2, which is going to be no more than 3 by 3, at most 5 by 5. And then using this guy T, transform the specs in your 2D into the specs for 1D filter H of omega. In other words, derive specs for H of omega from the specs in 2D. In 2D for H of omega 1 and omega 2, and given the T. You've already nailed down what T of N1 and N2 is. Either you chose it or you design it, and I'll talk about it a little bit more how you design it. So given that you know the T, given you know the specs for H of omega 1 and omega 2, you can come up with a set of specs for H of omega. And now we're doing the classic thing. Transfer a problem we didn't know how to do to a problem we don't know how to do. We know we have like a gazillion years of experience in designing optimal H of omegas. So in other words, we want to design omega S, omega P, delta S, delta P for H of omega. We want to come up with a set of specs for that. Once you have that, you can now design H of omega, or alternatively H of N, let's say using the optimal filter design, or in fact in MATLAB there's a Ramaise exchange algorithm you can use, etc. And then when you're done with designing H of N, you can combine H of N and T of N, T of N1 and N2, to get H of N1 and N2. And how do we do that? Well, it's the thing we started off with. H of omega 1, omega 2 is H of omega, where we replace cosine omega with T of omega 1 and omega 2. And you might say, well, where does McClellan come into this? Well, McClellan came up with a nice simple transformation technique, a 3 by 3 kind of a filter that he initially used for all his designs, but of course he also came up with ways of designing T. But just so that you have an idea, here is in particular, so I still didn't tell you how to design the T guy or where the T comes from, but McClellan transformation, besides the technique itself, there's also a particular T that he came up with, which takes on the value half, 1/4, 1/8, 1/4, 1/8, 1/4, 1/8, 1/4, 1/8. So this is it. Here we have T of N1 and 2 equals T of minus N1 minus N2. So it's zero phase, fantastic. And it also has fourfold symmetry. These are the same, and these are the same. So this is the kind of the transformation that McClellan started off with doing some of his filters. I guess I didn't finish this transformation technique, so on Wednesday I'm going to give you some examples of using this transformation and other transformation in designing actual 2D filters. So, Cindy, do you have the graded homework and the solutions? So don't forget to pick up all of these on your way out the door. And if you haven't handed in your homework, please hand it in.